All right. So earlier this semester, we were studying Ampere's law,
Hmm.
and we had gone through Gauss's law and kind of talked about how Gauss's law really only tells you about the electric field caused by some sort of symmetric charge distribution within the Gaussian surface, right?
Yep.
And that it doesn't account for contributions of electric field from sources outside of that surface. And so then when we got to Ampere's law, which is a little bit different in its formulation, and we got to solenoids, and I kind of walked you through the standard textbook proof. You were asking the question, well, we've only cut a sheet of some of the wire, right? We haven't cut the sheet for every possible angle. So, like, what about the contribution to the magnetic field from those other cuts, so to speak?
Yeah.
And I did not have an answer to that. Because in my mind, I'm like, okay, we're only finding the contribution of what's on the inside here. Now, that led me on a journey of having to prove Ampere's law generally because it shook my foundation, right? And of course, as usual with me, went off on a wild tangent and, you know, went way over here before coming way back. And so this is not a short journey to the answer to your question. We probably won't get to the answer even within this session, but we'll at least have a foundation to answer that question. So with that, I'm going to share my screen here. I've got a folder dedicated to you now. So, with this course idea coming up, this summer kind of seminar idea, I
Mhm.
wanted this to be almost like a dry run to that, where I'm going to record the sessions and maybe snip them up, put some things on YouTube, see if I
Okay.
can revitalize my YouTube channel. And
Sounds
so,
good.
yeah, last week I was working primarily on stuff for that course, and then I thought, oh, wouldn't it be fun if we walked through this? So this is pretty much all my free time for the last week was trying to take the exploration in Ampere's law and put it in some sort of a reasonable order.
Wow.
And so, are you able to see?
Yes, I can see.
All right. So I thought, like, where else to start with general Ampere's law than, with the piece that we always start with, which is the long straight current carrying wire.
Yeah.
So of course, the magnetic field, as with all physics, it's mostly experimental or observations that we then turn into mathematics. So I kind of wanted to
Mhm.
start there.
Okay.
So, at some point, and Ampere was certainly one of the guys who was figuring out how to collect charge on one side and pump it to the other side of the wire. And in doing so, they also had magnetic stones and compasses at the time. And so, holding a compass, the second you turn on current in that wire, the compass for some reason aligns perpendicular to the wire itself. No matter where you move the compass, it's always rotated to where it's perfectly perpendicular to the wire.
Mhm.
Um, and so that ends up giving us a picture of a magnetic field that curls around the wire. And in the case of the long straight wire, a good coordinate system would be cylindrical coordinates about the wire.
Sure.
And so, right, the magnetic field then always points in the theta hat direction and also happens to fall off in strength. So, using different apparatuses, they figured out that it falls off with a long straight wire. The field strength, or the kind of the magnitude of the vectors, seems to fall off with the inverse of the radius.
Yeah.
And so, with that, I'd like to make kind of like an ad hoc mathematical argument for why that's the case, why the field falls off as 1 over r in the case of the long straight wire. So because symmetry, right? There's certain things in nature that we call symmetric, and when something's symmetric, it means that you can't detect change. So when I say symmetry, I'm really talking about change that you cannot detect. So if you have this long straight wire, you got your eyeball over here. Let's see if I can annotate on this. Let's see. There we go. All right, so you've got your eyeball, and you got this long straight wire with constant current, and that's all there is in the universe according to this eyeball. So you can move to the right parallel with the wire, and nothing seems to change visually, right? There's always more wire of the infinite wire on this side, and there's always infinite wire on this side. So no matter how much you move to the right, the picture doesn't change. Same with the left. And so there's no way to tell what your z coordinate really is. So there's a symmetry along the z coordinate. Um, and then, of course, there's no way to orient yourself in a circle where you're at a constant radius. So, say I give you some sort of a B field meter and you can detect the B field strength. If you move in a constant radius circle, that B field strength is not going to change. So you'll be unable to tell, what an absolute theta would be, what an absolute angular position would be. So in that case, my argument for why the field has to fall off in this particular way is because the B field is really the density of magnetic influence spread over a cylinder in this case. So, the source of the B field is the current,
Mm.
and it's feeding every part of a cylindrical shell around it. And so if we consider the source quantity to be the current, which is the magnetic field source at a point, times the length of the wire, happens to be infinite in this case, but each point of current should count as an influence or a source of the field. And then we divide it by the cylindrical surface area that influence is being spread over, which in this case would be the circumference, 2 pi r times the length h, which happens to be infinite. So thankfully, we've got canceling infinities, and you just end up with the B field must be proportional to the current, which is the influence, the source, divided by the area it's spread over, which happens to be 2 pi r. And then, of course, you've got your constant of proportionality, which just happens to be mu sub naught. And you did an experiment in 212 that probably got pretty close to what that value is.
Yep, I remember that.
That was one of my favorites. All right. So far, I kind of expected at this point you would be like, yeah, I already know this, Isaac. Well, is there anything here that you want to point out or have questions on?
Um, oh yeah, the classic infinite wire. Um, yeah, this is a pretty cool one. Um, so could you maybe can you draw on this still?
Sure.
So when since it falls off with the radius, could you maybe draw us what this is just interesting to me. So this is the magnetic field, it's circular, and then would you just have like like layers of magnetic like how does this work exactly?
Yeah. So, use your right hand rule to get the B field curl direction.
Yep.
And it's kind of tricky with B fields because they do loop in and close on themselves to kind of visualize what a density of field lines would look like. But maybe how I would do it is I would say closer to the wire, there's a denser amount of field lines. Of course, field lines are just a way that we kind of think about the magnetic field in this case. But
Right.
you know, I guess the main argument is just because it's a symmetric system, the B field strength has to be the same everywhere azimuthally or on the theta direction for a fixed radius. And the idea that like the current, which is really the source of the B field, the source propagates outwards, right? And its influence spreads cylindrically. And so at any given point in time, it can only have it has a finite amount of influence that it has to spread over, a finite amount of surface area.
Yeah, pretty cool.
It's definitely harder to intuitively grasp than the electric field. Nice, you know, lines going outward radially.
Yeah, those were my favorite.
And also, this is why they say there are no magnetic monopoles, right? Or in other
Mhm,
words, Gauss's magnetic law, which is there is no magnetic flux through an
mhm.
enclosed surface. All right, let's see if I can move on to the next one. All right, so of course you can imagine I didn't want to have to draw these real time. Like, it takes a long time to draw.
Yeah.
Um, so And the next slide is just about magnetic vector fields and polar coordinates. And so when all sources of a magnetic influence are properly accounted for, each point in 3D space is imbued with a total net magnetic field vector. So both a field strength or magnitude of the vector and a pointing direction. And so, before I was kind of just focusing in on the B field at one point. But of course, this vector notation, if I want to know the B field, at some vector position r. So say I define a coordinate center, and then I have some vector r that points to somewhere I'm interested in the magnetic field at, then I can just plug in those vector coordinates and out pops my magnitude and my direction, which is always theta hat in this case, or an azimuthal direction that curls around. Um,
Mhm.
we're more used to doing it with Cartesian coordinates, but you can do it with polar as well. Polar makes more sense for this application. And so for a polar cylindrical coordinates, let's see, this kind of coordinate system requires different unit vectors, right? And the tricky part about that is when you're in Cartesian coordinates and you just have your x hat, y hat, z hat, it doesn't matter where you're at in space. Those coordinates are always pointing in the same absolute direction. Whereas with the polar coordinates, as you can see, theta hat does not always point in the same direction. Which does z hat always point in the same direction for polar?
Yes.
It always right. Z hat's a kind of our fixed direction for polar coordinates.
Uh-huh.
How about r hat? Does r hat point in the same direction at any location?
Um, yeah, it does, right? Because it's just kind of, I mean, yeah, like
It's
depends on
a
where you're at.
it's always outwards, but it does depend on where you're at, right?
Yeah,
So like up here, r hat points up.
yeah,
Down here, r hat points down. Um,
yeah,
and so
exactly.
both r hat and theta hat depend on where you're at. But there's another difference there, which is that as you're walking away, r hat is still a displacement vector in and of itself. So r hat is a displacement of one away from your coordinate center. Now theta is an angle, right?
Mhm.
So if you pass through some angle in your coordinate system, it really matters where you're at radially to figure out how far you've traveled, right? So if you're really close to the wire and you pass through theta hat, or you pass through an angle theta, you have traveled less distance than if you pass through an angle theta further away from
Mhm.
the coordinate center. And so for that reason, the displacement in polar coordinates for theta, you always want to make sure that you account for the radial scaling. So in other words, if you pass through some angle theta, the distance you've traveled depends on both theta and how far you are away from the wire.
Mhm.
and it's related by, right, r times theta.
Yeah.
Because if theta is 2 pi, then circumference 2 pi r, and it all works out. So there's three kinds of movement that you can do in this system through the magnetic field. One is a translation in the z direction, and that's pretty straightforward because z always points in the same direction. So as you move in the z direction, you can say that your small little bit of displacement is just equal to a small step in the z direction, and then z hat just indicates which direction that small step is in. Whereas your movement two, which is radial translation, right, you can step further away from the wire. And likewise, because r is truly a position, not an angle, it's a position, then the change in that position gives you a displacement. And so you just have dr times r hat gives you the translation in the r direction. But then because theta is a rotation, like we talked about, you have to account for how far away you are from the coordinate center when you pass through that angle. And so in that case, you have to say that a small displacement in the theta direction is really equal to r times the change in angle you had. And then theta hat just orients you. And so this is just another case. This pops up in Ampere's law a lot. It's just changing angle can lead to wildly different displacements depending on radius.
Mm-hmm.
And so just kind of setting up for magnetic circulation, which is really what this is all about. Ampere's law just tells us about magnetic circulation. That's really all it does. So when interacting with a vector field, especially when I'm going to say walking a displacement, so in other words, we're just picking a path to walk. A valid question in a vector field would be, on my walk, how much is the field aligned or opposed to me? And a good intuition is imagining that a vector field represents like a water flow in a body of water. And as you swim, the flow can either help or hinder you. It may help at some parts of the swim, hinder at others. But for a given round trip, we want to know kind of the sum of all the ways the flow interacts with you, whether that's helping or hindering.
Mm-hmm.
So if you've got your magnetic field over here indicated with the red arrows, and you're walking a path indicated by the dashed line, we're going to walk a round trip. And at each point, we're really asking the question, how much is the magnetic field pointed in my direction of travel?
Mm-hmm.
And so we will figure that out using the dot product, which represents figuring out how much of something is parallel to you. So it's like, okay, we take to find a small bit of that help or hinder from the field, we take the B field at that vector position and dot it with the step along the path we took. And, of course, that's similar to taking the magnitude of B, the magnitude of your step, and then cosine phi, where phi is the angle between the field and your step. So a helping field, right, is any angle between 90 and 270, where theta is between there. Or I'm sorry, phi should be either greater than 270 or less than 90. So you're kind of falling in that range where there's at least some magnetic field that's pointing in the direction you're taking a step. And then a neutral contribution would be a 90 degree or 270 degree, where there's no field component in the direction of your step. And then the hindering field is just when the B has some component that is opposing the step you're taking. Now, what's particularly weird about Ampere's law is, do you remember how the magnetic field interacts with charged particles? You remember that law?
how the magnetic field interacts with charged particles.
Yeah,
What's it called?
you've got it. It's a force.
Biot-Savart?
Close. That's how you calculate the B field. This is how you figure out its force on a moving
Oh,
charged
right.
particle.
Oh God, what was that one? Is it QV cross B?
Yeah, exactly. That's Lorentz force law. So what's interesting here is like as we're walking this path, there really isn't any helping or hindering. That's all just an analogy for what's going on here. In truth, this cross product tells us that the magnetic force always acts perpendicular to the field. So that's what's weird about Ampere's laws. It's just telling you about how much the B field is aligned with you on your journey. But the B field being aligned with you doesn't mean that the magnetic force is aligned with you. So even though I'm using that analogy of water flow, really Ampere's law is tracking this at this point seemingly worthless quantity called magnetic circulation. It's like I don't know why we want to know this, but maybe it'll help later. So of course, to find the overall help hinder effect of the vector field, we just sum all of the contributions, take a small step, figure out how much B is in line with you with the dot product, take another small step, see how much B field's aligned with you, and sum it to the last one, and then just proceed stepping until you finish the full loop and add up all the positive contributions, negative contributions, neutral contributions to that overall circulation. And there's, of course, a more convenient way to calculate the dot product than figuring out the angle, because as you could imagine, finding some function for angle for this particular path would be pretty brutal.
Mhm.
Finding the angle every time, not super convenient. Luckily, with the dot product, you can just multiply the x component with the x component, in this case, the r component with the r component, theta component of B field with theta component of displacement. It's got that r d theta in it because when you pass through an angle, the actual distance you've stepped depends on the radius and the angle. And then multiply the z component with the z displacement. So this is what a circulation contribution would look like in polar coordinates. Now we finally get to the fun stuff. Actually, not quite. There's a lot of fun stuff. We're just getting there.
All
Um,
right.
so now we get to kind of talk about the first inspiration for Ampere's law, and that is the long straight wire. So I want you to imagine you've got this long straight current carrying wire, and you pick some random path. So that's indicated in the green here. I'm calling it path one. And we're going to just do some of the calculus now. We know we can find the total circulation for that path by taking the B field at every point on the path and dotting it with the step that we're taking at that particular point on the path. So now we're going to, put the mechanics of the dot product to use here. We know that the B field caused by a long straight wire has no z component or has no z component. It has no r component because it curls around the wire azimuthally. So it doesn't have any r component or any z component. It only has a theta component, which we showed earlier falls off as 1 over r. So mu naught times the current time over 2 pi r, the influence over the surface of which it is spread. And then we're dotting it with our step. And every step we make in this coordinate system can have a radial displacement dr. It can have an angular displacement rd theta, and it can have a z displacement dz. Now with the dot product, you get the 0 paired with the dr, so dr goes away. You get the 0 paired with dz, so dz also goes away. And so the only thing that lives is this theta magnetic field times the theta displacement. And what's really interesting there is notice when we do that dot product that the radius cancels. The radial scaling from the displacement cancels with the radial fall off from the field decaying.
Right.
And all we're left with is this constant mu naught I over 2 pi integrated with respect to theta. So we can pull those constants out, and the integral of d theta is just the accumulation of angle change, right? If you add up
Yeah.
all the small changes in angle, you get the big change in angle. So this is what we're left with for circulation. And notice I did not assume anything about the path. I didn't have to parameterize it. I didn't have to tell you exactly what it looked like. It could be any old odd shape that you want it to be. And this holds true. But we do have to consider the fact that, say we're walking this path 1 I've showed up here. Notice that the B field, say you start at this point A, and you start your walk, and you're doing your little polar displacements. During this upper part of the path, B is pointed with you. And then you get to a certain other point, point B, and walking from B back to A, the B field is now opposing you.
Mhm.
And so we really have to
Mhm.
break up this integral into 2 steps. The total circulation is going to be the circulation walking from A to B plus the circulation walking from B back to A. And the only difference there is that the angle that you sweep out walking from A to B, call that delta theta AB, is the exact same angle that you sweep out as you walk from B back to A. There's only one difference. What would that difference be?
Uh, it's a difference in angle, right?
Yeah, I mean, it's the same angle, right? But
Yeah,
different,
but different sign.
yeah, different sign, exactly, different direction. So delta theta AB looks like it's probably positive with the counterclockwise convention, and then delta
Yeah.
theta BA is negative. So when you add both those up, you end up with a total circulation of 0. And so for all closed loop paths that don't encircle the current, in other words, the current doesn't pass through them, the circulation will equal 0. The field doesn't have an overall helping or hindering effect because it helps equally as it hinders.
Oh,
And so this is just a consequence of the circulation being only dependent on the angle change.
yeah.
And because doing a closed loop path, oh, by the way, I should point out, I've got this eyeball on the wire that's kind of sweeping out the angle. So it sweeps this way and then it sweeps that way. And it can only tell clockwise, counterclockwise. And it's able to tell that, hey, doing this full loop, I went counterclockwise a certain angle, I went clockwise right back. And so no circulation in this case. All right, now we've got the only other possible situation, really, fundamentally, which is what if the loop surrounds the wire? So in this case, we do the exact same mathematics. Dot product works out exactly the same, and you end up with the circulation is just mu naught I over 2 pi times delta theta. However, something has changed from the case where the loop didn't encircle the wire. And what is that change? What's different now?
Let me see. The angle, the angle, I think it's gonna get added instead of subtracted, right?
Exactly. So if you do like maybe this is your starting point A, the angle you sweep out, it's counterclockwise the whole time.
Yeah,
And it could go just 2 pi to get back to where it started. Um, and notice, like in this case, the B field is helping the whole way.
yeah.
It's helping less here than it was here, but it's still net helping overall. So this time, all we have to do is say, well, we started here, we rotated an angle of 2 pi. So we don't have to split it into two groups where it was going negative angle and positive angle. It's just one time around a full 2 pi. And that
Mhm.
cancels with the 2 pi from our magnetic field. And that just leaves us with mu sub naught I. And this kind of is the motivation for that weaker form of Ampere's law that works for this nice symmetric long current wire case, where the circulation is just equal to mu sub naught times I times n, where n is the number of times the loop winds around the wire before closing in on itself. So, for example, you could imagine a path that goes around twice before it stops where it started. That would give us 4 pi for delta theta. And so then n would be 2 because we've wound around this thing twice. And we've gotten twice the helping effect from the B field as before. N could also be negative if we travel against the field the whole time. So if we
Yep.
imagine we go around this way a couple of times, you'd get negative 4 pi. And so, yeah, now there's an interesting example here that's going to help us later on with the general case,
Okay.
which is, here we're starting at A and we walk, walk, walk. We're getting helped by the field, helped, helped, helped. We're even passing 2 pi at this point. By the time we get to point B, we've passed 2 pi. But then we turn around and we walk back. Now the field hinders, 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 hinders all the way back till we get to point A. So in this case, we've certainly walked around the wire once. We've also walked the other way around the wire to get back to where we were.
Right.
So the circulation is still zero. The circulation is not going to be foolable here. It only detects true threading. So that's what we're going to call this. When the current pierces that loop, we call it a threading event or a linking
Yeah.
relationship. And in the case I have drawn over here, do you think the wire is threaded or linked by the current?
Which case? This one up here?
Yeah, over down here on the left. Would you say
No.
that that wire is threaded or linked with the loop?
No.
No. Why not?
It's there's like a hole right here.
Yeah, right. You can actually move the wire out of the path without passing through the path, right?
Yeah.
And so we consider this not linked. Now, if I put the current here, what do you think then?
Oh, now you're good. Yeah, you can it shouldn't be zero.
Now you are linked, and there is just going to be N equals 1 Ampere's law because we're getting a helping effect, helping, hindering, helping. And we got a lot more helps than hinders along the way. But it's so interesting that the dot product and the way the field decays, it doesn't really care about what the loop does. All it cares about is the change in the angle. And so it doesn't matter how complex of a case you throw at it. If the wire goes through the loop in a way that can't be undone without breaking the loop, then you're going to have a linking or a threading, and the circulation is going to be proportional to the current going through it. And if the current's outside that loop, there's going to be no circulation, no matter how complex it is.
I have a question.
Yeah,
Uh, so I just took Calc 3. This kind of reminds me of Green's theorem with the simple closed curve idea, like
yep.
line integrals. Is that kind of
Very,
similar?
yeah, very similar to Green's theorem, Stokes's theorem. And actually, there is a tie-in. I don't have it mapped out at this point, but Green's theorem and Stokes's theorem is what can take Ampere's law from a global form, like we know it from class. This would be a global form of Ampere's law. And using Stokes's theorem, you can write it in what's called the differential form,
Right.
which looks something like this. So this tells you what happens at the infinitesimal scale of a tiny little volume element. Whereas this integration version, the integral version, tells you what happens universally. Um, and so you can jump between either of those two forms using Stokes's theorem.
So cool.
It definitely ties in. Of course, the global form of Ampere's law is more of what you have to prove, because when you run experiments like this, like we can't experiment on the infinitesimal scale.
Right.
So we're stuck with this messy global system that we have to simplify. And then we can use Stokes's theorem to say, hey, every little volume of space must obey this. And so it's interesting because this is the much more simple version, what happens in a tiny little volume of space. But we have to go the long route and prove the harder case first. I tried to do it the other way. It's not.
Oh yeah.
I spent weeks trying to just prove it on the infinitesimal scale, and I just couldn't do it because I was trying to bound errors, like trying to show that the error from nonlinear terms shrunk faster than with linear terms. And I couldn't do it. And ultimately, I decided to take the global route.
You said error? What do you mean? You said
Oh,
errors?
sorry, error.
Errors.
Yeah.
I got it. Okay.
So I was doing something called error bounding,
Okay.
where you're basically trying to show, if a small element has an error, say on the order of, I don't know, delta H or something, where the width of the patch is delta H, then as
Okay.
you grow as you grow the system, you add more infinitesimal elements, the error will scale with how wide the system is.
Gotcha.
Sometimes it can scale with the area of the system, sometimes with the volume. We'll be talking a lot about that in the course this summer is error bounding and why that's fundamental to calculus
Okay.
and why it works.
Great.
Um, Error is
That's
super
exciting.
important, but I was not able to use it in this case. And I tried because I did not want to, because I remember this proof that I'm going to take you through is something that I was taught in E&M, but it was not explained very well. It made no sense to me.
Gotcha.
There was a lot of hand waving and just vector notation and
Hmm.
well, we know this and we know that, and I'm sitting there like, I don't know that. I don't know what you're talking about. I don't know that at all. Always get those moments in class where the teacher's like, "We know that," and I'm like, "Do we? I don't know. Pretty sure I don't know." So this is just kind of a tie through of everything we've talked about,
Okay.
which is that it doesn't really matter what path you take for the specific field generated by a long straight wire. It's only the change in angle that contributes to circulation. The way I kind of talk this through, though, is say you're walking from point A to point B, and here's your current wire that's generating the field. Well, walking from A to B, you're pretty close to the wire, right?
Mhm.
So the B field is stronger.
Yeah.
However, you're closer to the wire, so walking through the angle makes for a shorter path. And likewise, if you walk from, say, point C to point D, you're further away from the wire, so the field is weaker,
Right.
but you're walking a further distance, so more distance for the field to be in alignment with you.
Hmm.
Now, just a picture like this doesn't guarantee that those effects are going to cancel out and make the circulation only theta dependent. That's where the math came in, right? When we saw
Hmm.
this r d theta cancel the radius with the mu naught I over 2 pi r, what that was telling us is that the field decays at a rate of 1 over r, and the length increases at a rate of 1 over r, or I'm sorry, at a rate of r. So in other words, you've got an increase with r, you've got a decay with 1 over r. And so just for this specific field, it works out to be only angle dependent and not even like a definite angle. You can go beyond your angle bound. You can go way over here. It doesn't matter. As long as you end right here and you pass through a net delta theta, that's the delta theta that matters. So
Right.
this is cool. It only depends on initial and final, right?
Yeah.
Very, very calculus, fundamental theorem of calculus esque, right? We've got it only matters where you start and stop.
Yep.
Everything that happens in between is irrelevant to the calculation, which is super baffling that would be the case. Now we get to go to, all right, we focused on the long straight wire. That seemed to work out really nice. What about any wire, right? Like we can't just test Ampere's law for straight wires and then call it a fundamental law of nature.
Right.
So we've got to get to some complicated curvy stuff to really prove Ampere's law. So let's see here. So you learned the Biot-Savart element. What Biot-Savart did was said, hey, let's take the smallest little bit of current you can imagine and try to figure out what the field produced by that small current would be. And so what they came up with, mostly empirically, so through experiment, is you've got this small little length of wire. We call it, I'm going to call it DW for a small little length of wire. And
Sure.
it's got current I flowing through it steadily. And as it turns out, the relation, the B field contribution varies
Hmm.
with the length of the patch divided by the radius squared, the distance that the wire segment is from wherever you're measuring the field at. But then there's also this angular component as well. So in other words, here's radius r, and here's say a B field caused by this small little bit of wire. And if I keep the same radius, but slightly rotate my angle towards being more parallel with the wire, even though the radii are the same, the field is actually weaker because your phi has decreased from 90 to, I don't know, like maybe 60. And so this is not a nice spherically symmetric field like we're used to with for the electric field we have the point charge.
Hmm.
And the field is nicely spherically symmetric. The E field at some given fixed radius away from the point charge is uniform.
Hmm.
Not the case with the Biot-Savart wire element because it has some directionality that's intrinsic to it, right? The current, the source is flowing this way. And so the field actually kind of, if I were to draw equally strong B fields, it would look kind of like almost like a half circle. So every point on this line I drew, say, has an equal strength B field. And notice as the angle gets smaller and smaller, you have to get closer and closer to the wire element to get an equivalent B field strength.
Hmm.
And that's where that sine theta or sine phi comes in. So I did an art project and tried to tried to represent what this kind of shape would look like because the B field curls around. Like it's still azimuthal, that's nice. The field is still always in the theta direction from the coordinate system, but it kind of like this equal strength B field almost creates this like apple looking shape,
That's
right?
cool.
Like a donut with no hole.
Wow, that looks cool.
But this is all experiment. You know, this wasn't. They call Biot-Savart almost like an axiom of electricity and magnetism, right? It's kind of this building block that you accept and move on from. And
Yeah.
it is definitely consistent with the other laws of electricity and magnetism, but it's certainly different than a point charge, right? Like way harder than a point charge. And this is why I think magnetic fields are in general more difficult to understand, is because you can't really take a B field source and turn it into an infinitesimal point. Like
Mm.
with a charge, you can do that. You can have a plus 1 Coulomb charge and it's got this nice symmetrical field. Now, my question for you would be, is it possible to have a tiny little infinitesimal length of wire that carries constant current?
Is it possible?
Yes.
Why? Where's the current coming from?
Isn't the current coming from the changing B field? Or is it just coming
Actually,
from
oh,
like a
that's a great
source?
point. But we're dealing with just magnetostatics. So the B field
Uh,
we're assuming is constant, and it's generated by the current source, which is constant current. So I guess what I'm asking is can this wire element exist by itself?
Yes.
Where does the current come from? Where's all that
Doesn't it
charge
come
coming from?
just from like a battery or something?
Okay, I see what you're saying. You're like, hey, if I like hook up a battery right here, then I could drive the current.
Yeah.
That's fair. You're not wrong. You could. But then you've got wire going this way and wire coming this way.
Right. Okay. I see what you're saying.
Right? So in other words, like this current element, the Biot-Savart current element can't exist on its own. It can't exist
Okay.
because it needs a closed loop to drive the current. Because current is just moving
Right.
charge, and fundamentally, charge cannot be created or destroyed.
Hmm.
And so, due to current continuity, you need to have infinitely many of these little wire elements connected in some
Okay.
sort of a loop, right?
Yeah.
But you're right, you could hook a battery up to it.
No, I see what you're saying though.
So let's see here. We've got so anyways, that's Biot-Savart, and that's going to be one of our axioms for trying to prove Ampere's law for curvy current wires. Now, what's really interesting is with the infinite long straight wire, the field fell off as 1 over the radius, right?
Yep.
But with Biot-Savart, we go back to the field falling off is 1 over r squared. My explanation for why that is even though it's not nicely spreading over a sphere, right? The influence isn't nicely spherically spread. It's kind of like donut spread or like apple spread, right? But it's still spreading over a closed volume or like a closed surface area. Whereas before it was closing over this cylinder that had a source at every point along the way. So here we have a finite source spread over an increasing area. That in that area that it's spread over is related to r squared. It's not a 4 pi r squared. It's not a nice sphere, but it's somewhat related to that.
Okay.
So that's where the sign comes in, is to deal with
Yeah, okay.
the non-spherical nature of how it spreads its influence. So, okay, we've got the wire infinitesimal falls off as 1 over r squared. So does Ampere's law hold for wire infinitesimals? It'd be nice. I'm like, that'd save a lot of time.
Right.
But let's think about Ampere's law and what it says. And you tell me if you think that this little wire element is going to obey Ampere's law.
I think no.
Why not?
It has to do with the current.
What particular about the current? I
It's
mean,
just
we
kind of
kind
like
of, oh, go ahead.
it's just like not connected to anything else.
True. So we already agree, like, this element can't even exist in reality, right?
Yeah,
That's already a problem. But now I'm going to
exactly.
ask you to assume it could exist.
Okay.
Would it obey Ampere's law? So in other words, if I walk a path, if I walk some sort of a loop around it, will the circulation only be proportional to the enclosed current or the encircled current by that loop?
Yeah, I don't see why not.
Okay, so let's think about a few questions. One is, what was the field strength for the long straight wire that allowed that cancellation? Or I guess, how did the field fall off?
1 over r.
And how does the field fall off for a Biot-Savart element?
1 over r squared.
So when we multiply that by our r d theta,
Mhm.
only one of the r's cancels.
Right.
And now you're left with a field that does depend on, or a circulation that does depend on distance, not just angle. So that's the first problem with Biot-Savart and Ampere's law. The second problem comes from this question, which is, how would you even determine what threading or linking looks like? Because if I have a loop here, like surely I can move this wire element out of the loop without breaking the loop, right?
Right.
So it's like, what does threading even look like? Like, how can I say what an encircled current is?
I don't know. That's weird to think
Exactly.
about.
It doesn't make any sense, right? It's like
Yeah.
to be encircled, you can't pull the loop away from the element without breaking the loop. That's what it
Right.
means to be linked or threaded.
Right.
So it's like two issues with Ampere's law for this little infinitesimal element. Now, this is frustrating because with Gauss's law, you remember we could do a little dq. We could take a
Mhm.
little bit of charge, and that little dq obeyed Gauss's law.
Mhm.
The flux through the enclosed surface, it was based on the charge. So this is a case where Gauss's law for electrical fields works for the infinitesimal element of the electric field, but Ampere's law doesn't work for the infinitesimal element of the magnetic field. So it's a problem.
Yeah.
And I kind of just, from what we talked about, I'm showing why it's a problem. So like I said initially, it's a problem because the field falls off now as 1 over r squared. And so that same cancellation doesn't occur, right? When we do the dot product here, we end up with this nasty integral that not only depends on 1 over r, or the distance that the walk is away, it also depends on the angle between the field and the wire element. I'm sorry, the angle between the B field and the path that you're walking. So it's like this is a horrifying integral. Definitely not going to reduce to just a change in angle. And so we pretty much already talked over most of what's on that page. Now we get to, well, we get to the part where we talk about our setup, like how are we going to solve this problem? And it's funny because I've got like 3 layers of annotation here. Like I would annotate it and then I'd be like, oh, I'm not happy with that. So I'd annotate it again and then take a screenshot of it. It's pretty trashy, but I did my best.
That looks good.
Oh, look, my stupid head's in the way. All right. So in order to obey current continuity, right? Current can't be created or destroyed. It has to be transferred. We're going to restrict our proof to wires that are closed loops. So in other words, whatever current wire we have needs to close in on itself.
Okay.
That way the current continuity can be upheld. And so for that wire, I'm going to do a parametric path, right? Very Calc 3. So we take a vector called W, that's a parameter of time. And we tell you exactly where the x component of the wire is at some point of the parameter t, exactly where the y coordinate of the wire is for the parameter t, exactly where the z coordinate is for the parameter t. And we allow t, our parameter that sweeps out the wire, to run from t initial to t final. And that is a full parameterization of the curve. So in other words, if this is when t is t initial parameter, we run the parameter t, it sweeps out our wire, and by the time we've done one full loop, our parameter is to t final.
Okay.
So that's the setup for how you can tell where the wire is. We do the same thing for the amp loop, or the path we're walking, trying to find the circulation over. We use a different parameter s, and we pretty much do the exact same thing, require it to be a closed loop. It's important with Ampere's law to remember that the Amperean loop is not necessarily a physical object. It's just an imaginary path that we draw in space that we want to calculate the circulation for. Just trying to figure out how much the field aligns or disaligns with our path. All right, so we've got our parameters chosen and the vector, right, that separates a point on the wire and a point on the path. I'm going to call that R. That's super important because Biot-Savart requires us to know the radius vector in order to figure out the field contribution at some point in space. And the field we're interested in is only the field that is on the path, right? Fields made by the wire, and we're calculating the circulation on the path. So that's what matters to us. So we find the radius vector by saying that, well, the wire vector plus the radius vector must equal the path vector. And so we get wire plus radius equals path, then we rearrange and we get the radius vector is just the path vector minus the wire vector for any chosen parameter s and t, as long as it's within our loop bounds for that parameter. Because there's so many different ways to pair this up, right? Like I picked this wire point. There's infinitely many path points that I could point to for this particular wire point, right?
Yeah.
So really I have two smooth parameters s and t, and I can pick any s and any t, and that will relate to some point on the wire pointing to some point on the amp loop.
Okay.
And yeah, Biot-Savart tells us that the magnetic contribution from this infinitesimal length in wire, which we call dW, is equal to mu naught I over 4 pi times the wire element cross product with the radius hat vector divided by r squared. So that's how we find the small contribution to the magnetic field caused by wire element dW. So in this case, we might have a little dB pointed like that. However, to find the total magnetic field at this point on the path, what do I have to do?
Integrate.
Got to integrate.
You
I
gotta
got to,
integrate.
right? I got to figure out what's the B field contribution by the next dW. What's
Exactly.
the B field contribution by the next dW? And do that for the whole wire loop. And that will give me my total B field at only a single point on the amp path.
Right.
It's a lot of work for just one point of the infinitely many we need to calculate circulation.
Wow. Yeah, you're right.
Nuts. Seems impossible. So you're
Wow.
right. We've got to integrate. So we integrate. And this is how you find the magnetic field at a single point P of S caused by the entire wire.
Oh boy.
Now, I'm really hoping to write like a Python or MATLAB code for this because I think it would be pretty cool. Um, but if you really wanted to go all in with the parameterization, you can write dw, the vector, using the chain rule as dw vector over dt times dt.
Okay.
And then you can integrate the scalar parameter t as opposed to integrating with some vector element. And they do that a ton in Calc 3, right? You almost always end up integrating in t, right?
Yep.
All
Yep.
right. So that's how hard it is to find the field at a single point. All right, next up, we got to find the circulation. And to find the circulation, you have to integrate the full wire to find the magnetic field at a single point, right? That's what this is. This integral just finds the B field at some point on the Amperian loop. Then once we find the field, we dot it with dP to figure out how much that field is in alignment with the particular path step we're taking.
Right.
That's the outer integral. Because we've got to integrate, right? We've got to figure out how much is B pointing in dp here, how much is B pointing in dp here, how much is B pointing in dp here, how much is B. And every time we do that, every step we take, we have to integrate this damn thing again.
Oh,
So it's like it's a for loop is what it is. I mean, we've done lots of double integrals, but this is the first double integral I've worked with that it's a for loop. So it's literally do this integral, then dot it with dp, take a step, do that integral again, dot it with the new dp, take a step, do the integral again to find b, dot it with dp, so on and so forth.
oh man.
Brutal. All
That's
right, so
awesome.
to get the total circulation, you have to do a wire loop integral an infinite number of times to do the path integral and find the circulation.
Oh boy.
Yeah. And at this point, most people would just give up,
Right.
right? Like, no, this isn't possible.
Uh, and look at that integral too. That integral is not easy, so it's not like you're doing an easy
No,
integral every time.
right. And not only that, we're trying to prove this generally. We don't even know what W of T and P of S even are. We're trying to do it for every possible configuration of wire and loops. There's another layer of infinity. We've got infinities on infinities on infinities. So we need to look for a way to cut the complexity, right?
Yeah.
And honestly, this slide is pretty much just the desperation slide that we talked through. So I'll skip that one. We got to break it down piece by piece,
Yeah. Make it easier.
make it easier. All right. So the first step is we're going to try to mix these integrals a bit. So there's a little bit less of a for loop going on.
Okay.
And how I'm going to do that is I'm going to argue that I can distribute the dot product in to the dBs. In other words, I don't have to add up all the magnetic field contributions
Okay.
before I dot with dp. And my argument for that, I'm going to keep it to a finite basis. So imagine you have some vector A added to some vector B. So vector A plus vector B maybe looks something like this. I want you to notice that the projection of A in C's direction, right here, plus the projection of B in C's direction is the exact same as the projection of A plus B in C's direction. So in other words, the dot product is distributive.
Right.
And I can distribute dot C to A and dot C to B.
Yep.
Because of this picture, you can stack as many as you like. So because this inner integral is saying, hey, you need to sum up all the B field contributions for this single point in space and then dot it with dp. I'm saying, let's dot it with dp for every little dB we find. Let's just say, here's this dB for this point, dot it with dP. Here's this dB for this point, dot it with dP, and then add them all together. And that's going to be equivalent to as if you found the total magnetic field at that point and then dotted it.
Okay.
So dot product gets distributed inside. And that results in an integral that now looks like this once you pulled out the constants. So we still have to do this kind of for loop integral, but we've moved the dot dp inside. So it's still equally as daunting. Doesn't seem to have helped that much, but it will in the next step. But it is pretty cool because, you know, like, I don't know, when I'm in class, normally people are like, oh, the dot product distributes. And I'm like, cool, why? And the reason why is because when you stack vectors tip to tail and you take the projection of the stack, it's the same as adding the projections of each individual vector. Gives you the exact same result.
That's awesome.
That's why the dot product distributes. All right. This is the real breakthrough here, this next step. So it's something called the triple scalar product identity. Are you familiar with this?
Yes,
Yeah. So
indeed.
we're looking here and we've got dw cross r dotted with dp. These are all length vectors, right? dw is the displacement of the wire, r is the distance between the wire and the path point, and dp is the displacement of the path. So we're going to make use of a geometric interpretation of the cross product. For two vectors A cross B, their magnitude is equivalent to the parallelogram area. And so A cross B tells you the area within the parallelogram that those two vectors define. And then when you dot it with C, it actually gives you the volume of this parallelepiped. So exactly how that works, I don't think we have enough time to dive into, but it is a pretty, like, it's a, you get A cross B, it points, upwards like this because cross product's always perpendicular to both A and B. And then when you dot it in C's direction, it deals with the slantedness of the parallelepiped, right? Like there's going to be more enclosed volume if C is straight up and we've got a cube than there is if C is slightly angled and the parallelepiped is kind of sheared like that. So now we're going to look at a way we could write this equivalently, this triple scalar product that might make our lives a little bit easier. So notice that A cross B, and the right-hand rule is super important here because direction matters. So A cross B points up.
Yep.
Dotted with C, is that going to be positive or negative for this picture?
Positive.
Positive, right? Because A cross B has a component that is parallel to C. So whatever way we mix up this triple scalar product, we want to make sure that its result is positive. And we see that C cross A dot B, C cross A should be going into the board or out of the board?
Into the board.
Into the board.
Cross A.
Cross A. And then B, like it definitely has a component in B's direction. B's got a little bit into the board. So that's also positive. And we know the volume of this parallelepiped is the same no matter how you measure it, right?
Yep.
Doesn't matter what crosses what first. It's the same parallelepiped. Got to have the same volume. So as long as we keep the sign conventions fine, we could orient it this way. You can also do B cross C dot A. And that'll give you positive as well. Now the magnitudes of all of these are equal, but we want the orientation, we want the direction to match. Because notice this directionality matters for our integral here. If dw cross r is positive at a specific point in the integration, that, and it's in the parallel direction of dp, this integral is going to spit out a positive value to some. And if it's anti-parallel, it's going to spit out a negative to some.
Okay.
So we're going to take this integrand and rewrite it like this. With the two infinitesimal elements sharing the cross product and the radius being the thing we're dotting with.
Okay.
Now, we could have noticed this even before this point, but what's the dimensions of dp? Going back to physics 211 here.
The dimensions,
Yeah,
like
remember
like what,
dimensional analysis, right?
right? Like what units does it have?
Dimensions aren't quite units, remember? It's like unit would be like meter, centimeter, but dimension would be
Length.
length, right? So dp
Yeah,
has dimension length. A
yeah,
little bit of wire also has dimension length.
exactly.
R has dimension length. And then r
Yeah, or
cubed in the
cube.
denominator has a dimension length cubed.
Yeah.
So this integrand is dimensionless,
Oh shoot.
which is great. As you remember before, the way we got Ampere's law to work with a long straight wire was with a dimensionless integrand. The R canceled with the R. Something similar is happening here. So that's our first hint that maybe this isn't as hard as it looks. The integrand doesn't care about how far away the wire is from the loop at any given point. So
That is nice.
that's pretty cool. Now we've got to
Yeah.
explore what the hell that even means, because that looks
Huh.
pretty complicated still.
Yeah, let's do that.
We're getting closer. All
It's a lot
right.
of fun. A lot of fun going through this.
It's interesting, right?
Yeah.
It is interesting, but it was a lot of free time. Yeah, this was probably the hardest thing I've ever worked through.
Oh wow, really?
Yeah.
Huh.
Yeah, I couldn't find anything online that was at my level, if that makes sense. Like
Mhm.
I could find some stuff that was like severely advanced, where I was like, I don't know what they're talking about, right? This is a math class I haven't taken. And then, I could find some stuff that's like, for the straight wire, this is what happens. And I'm like, I already know that.
Right.
I needed
Can't
to
find
find
that.
a middle ground.
Right,
Um,
yeah.
so we can take this integrand. I'm going to start writing it with r hat instead of r vector over magnitude r vector,
All right.
just because I think it makes it a little bit easier.
All right.
So we rewrite the integrand this way. We've got dp cross dw, a small element or a small displacement on the path cross a small displacement on the wire, dotted with r hat, a unit vector, right? Funny enough, unit vectors are dimensionless, right?
Yeah.
Because it's length over length.
Yeah.
So unit vectors, they're called unit vectors because they have the unitary length of one, not because they have a dimension assigned to them. So where the triple scalar product used to represent the volume of a parallelepiped, when each constituent vector had dimensions of length, now it represents a parallelogram area projected onto the surface of a sphere. So I don't expect you to buy that offhand,
No, I
but kind
actually
of
do.
cool, right? I love it.
Yeah.
So my idea now is once again, we're going to put an eyeball on the wire and we're going to imagine taking a step on the wire dw and looking at a specific point on the path with infinitesimal length dp. And we go ahead and stack dp and dw tip to tip, and we create this parallelogram area. This parallelogram area is dp cross dw,
There we go.
okay? Then the radial unit vector always points in the direction the eyeball is looking.
Mhm.
And so when you dot this area with the radial vector, it actually projects it onto the surface of a sphere.
Look at that.
And then the radius of r magnitude squared, that's actually exactly how areas scale, right? Like, for example, if I take something and I've got it 1 meter from my head and I move it 2 meters from my head, it will appear to have decreased in area by a factor of 1/4 because I doubled the radius and I decreased the area by a factor of a fourth because the length scaled down by a factor of 1 over r, so the area scales down by a factor of r squared.
Right.
Also, it kind of shows up in the fact that, right, the surface area of a sphere is 4 pi r squared. And so what this denominator is doing is it's taking this spherical patch that we've projected and it's scaling it down onto the unit sphere, the sphere where radius is 1.
Okay.
And so that's what our integrand represents, is my argument, is it represents a small bit of area on a unit sphere. Basically, when we think about this, we think, total field of vision that I have is kind of like a spherical dome, right?
Uh,
And there's 4 pi steradians in that dome. Have you ever heard that term, steradians?
Not really.
So radians is measure of angle.
mhm.
An angle is kind of like apparent length, is what I call it. Because, you could take a dime and hold it up to the sun, and you can cover the sun with the dime,
Right.
right? So the second I cover the sun with the dime, both the sun and the dime have the same apparent area.
Right.
Of course, they have different areas, but the
Mm,
apparent area is the same.
Right.
And that apparent area that something takes up in our field of vision is something called solid angle.
Okay.
And solid angle is basically the extension of regular angle, right? Regular angle ties to length,
Mm,
solid angle ties to area.
okay.
So what this integrand is really measuring is a solid angle.
Okay.
All right. I feel like I'm like talking about things on the next slide before I get there, which is fun.
Mm,
Then I get to the next slide and I'm like, I don't need that slide. But I do kind of want to talk about apparent length a little bit. I think it's
Okay.
going to be important. Are you able to see?
Yes.
Cool. So once again, like the idea of a solar eclipse. I love solar eclipses. It's just so convenient that the sun is 400 times further away, but 400 times larger than the moon. And it works out just perfect to where the moon at the right time can just perfectly cover up the corona of the sun. Or I'm
Right.
sorry, can cover up the photosphere of the sun and you can see the corona. Like that is like, I don't know, have you ever seen a solar eclipse on Mars?
No.
It's like its little tiny moon is, barely covering the sun, right? Like, we definitely lucked out on Earth.
Yeah.
So apparent length is really angle. That's what angle is. It's apparent length. How long does it appear to me to be? Not how long is it? How long does it appear to be? And for small angles, as we've already talked about, for small angles, you can say that the distance, or I'm sorry, that the distance or the diameter of the object is equal to the distance times the apparent length or the angle. So this works for small angles. If you want to know the true diameter of something, like if I want to know the true diameter of the sun, I need to know how far away the sun is. That's its radius. And I need to know what its apparent length is. That's its angle, the angle that
Okay.
it subtends. All right, so doing it with vectors is a bit tricky. Um, but imagine you have an eyeball surrounded by a unit sphere, and it's looking at some vector v. Really, the only part of the vector that contributes to its apparent length is that part of the vector which is perpendicular to the radius, right? So, I take a pen. It looks pretty long now. It looks shorter. It looks a lot shorter. Now it's extremely short. So really,
Right.
it's only the perpendicular part of that vector that you can even see. So the first step is we've got to take that vector and just find the perpendicular component of it to your radius of vision. And you can do so if you know what the true vector is. You can subtract the radial component, and then that'll give you what's left over is just the perpendicular component. The tricky bit of looking math here, but all the vector dot r gives you is the component radial, right?
Hmm.
And then we just tack an r hat onto it because that's the direction it's in. So it's like the magnitude of the radial component of the vector is this. And then since it's a vector equation we're writing, we just tack an r hat on because that component is pointed in the r hat direction. And then we relate that to apparent length. So apparent length, or the angle that an object subtends, or a vector v subtends, is equal to its perpendicular length divided by radius. So in other words, if I have the pen a meter away and I move it 2 meters away, it will appear to me half the size or half the length as it was.
Mhm.
So apparent length and area are very crucial to this integrand. And you can imagine now kind of getting into 2 dimensions with solid angle, it's going to be two apparent lengths multiplied together to get an apparent area. Oh, I cannot seem to get that right. There we go. All right, so for solid angle, I'm going to start with the idea of apparent length. When you're in 2 dimensions, you really have 2 pi radians of apparent length, right? Like the
Mm.
most an object could take up in my field of vision is a full 2 pi.
Right.
And so we define apparent length or angle as the arc length, a circular arc length, divided by radius. Because a full circle has 2 pi r of arc length, delta theta full is just 2 pi r divided by r, which is just 2 pi radians. So it
Right.
doesn't really matter how big something, it doesn't matter what its radius is. If it surrounds you, it's taking up 2 pi r radians.
Mhm.
Whether it's a hat or, a mountain range, it's all
Mhm.
2 pi radians. So solid angle is very much the same, but instead of converting circular arc to angle, it converts spherical cap to solid angle or apparent area. So for solid angle, we define that as the perpendicular area of an object. So the perpendicular area an object takes up in our vision divided by the radius squared. Because for a full sphere, there's 4 pi r squared of spherical cap, right?
Mhm.
And so by dividing r squared out, we're left with 4 pi steradians of solid angle. So, the room I'm in right now is taking up 4 pi steradians of solid angle. because no matter where I look in this three-dimensional world, everything that surrounds me is the room I'm in. So the room must be taking up 4 pi r squared steradians.
Okay.
But it's only the perpendicular area that counts. So you have to imagine taking the walls and somehow projecting their area onto something of equal radius,
Um,
kind of get it into that spherical system. So for a small vector parallelogram with area u cross v, it gives us an oriented area vector, uh, like as shown over here, u cross v, and dotting it with r. That's how we get it to be a spherical cap. By the way, I have to keep saying this approximation only works for very small patches.
okay.
Patches so small on a sphere that they appear locally flat. Right? So like I'm on Earth right now, it's spherical, but where I'm at, it looks flat.
Right.
So
Okay.
that's the kind of setting this approximation must work within. So u and v have to be very small for u cross v dot r to give us an approximate area of the spherical cap,
Sure.
which I'm calling a perpendicular.
Okay.
Then you divide by r squared, and that removes how the spherical cap area scales with radius. And so what that does, like I mentioned before, is it projects, it basically takes the object you're looking at, the plane you're looking at, and it projects it onto the unit sphere, the sphere of radius 1. And then using apparent length, we can verify this. So my lemma is this, which is that instead of taking u cross v from the start, why not take the component of u that's perpendicular to the radius?
Sure.
Then take the component of v that's perpendicular to the radius.
Sure.
And then take u perp cross v perp. And that should give us that same spherical patch.
I see.
And then, of course, dividing it by r squared should give the same thing. So my argument is that u cross v dot r is equal to u perpendicular cross v perpendicular.
Mhm.
And then I'm going to use that decomposition into parallel and perpendicular to radius components. So u vector can be written as perpendicular u component plus parallel u component. V can be written as perpendicular v component plus parallel v component. Before we move on, how comfortable do you feel with this being the parallel u component?
Um, I think it's fine, but why do you multiply by r hat again?
Yeah. So right here I've written u perpendicular as a vector, right?
Uh-huh.
So I've got u perpendicular as a vector. And when I take the full vector u and dot it with r hat, I'm projecting u in r's direction, right? So
Right.
that's my u dot r hat. But the dot product returns a vector or a scalar?
Scalar, of course.
Returns a scalar. So if I want to have this written in vector form, I need to tell you what direction that
Okay.
parallel component is going. And that's why I tagged
Gotcha.
on an r hat.
Okay. Yeah. Then yeah, I think
That's a
that
good,
makes
that's a
sense.
good question.
Yeah.
Because I feel like the next step is kind of worthless mumbo jumbo without that. All right, let's see here. Can you see this?
Yes.
All right. So we can write u in decomposition into perpendicular and parallel and v in the same way. And my lemma that I'm trying to prove is that u cross v dot r is nothing more than u perpendicular cross v perpendicular.
Right.
So I start with one end, the u cross v dot r. I write my u vector in terms of perpendicular and parallel components. I write my v vector in the same way, perpendicular and parallel components, and then I'm dotting that cross product with r.
Sure.
Now the cross product does distribute, so I can distribute this with that, this with that, this with that, and this with that, and do 4 individual cross products.
Sure.
So I've got u perp cross v perp. I've got u perp cross v dot r hat plus u dot r hat cross v perp plus this last one is u dot r hat cross v dot r hat. R hat cross r hat, it's got to be 0 because r hat and r hat are in the same direction.
Uh-huh.
And when cross product puts parallel items to 0 because there's no parallelogram area being enclosed if 2 vectors are parallel. So that component goes by very nicely. This component's a little bit harder. We'll look at the cross product in here and say, well, I know u perpendicular is perpendicular to r hat by definition, right? So if u perpendicular is perpendicular to r hat, and I'm crossing it with r hat, one definition of the cross product is that the cross product must be perpendicular to both of its terms, right? So A cross B must be perpendicular to both A and B.
Right.
So U perpendicular cross R hat must be perpendicular to R hat. Because R hat's part of the product.
Right.
So it's got to be perpendicular. So then when I come in and dot with R hat, I've got a vector that has no component in the R hat direction. So that term goes bye-bye as well.
I see.
And same over here. You know, this product has to be perpendicular to R hat. So when I dot it with R hat, I get 0.
0. Wow, that's
So
cool.
all we're left with is U perp cross V perp dot R.
I see.
Very, very close, right?
Right.
But we don't want the dot R. So you need to
No.
figure out a way to get rid of that. Well, what we can say is both U perp and V perp are perpendicular to R hat by definition. So their cross product has to be perfectly parallel with R hat.
So it's just one.
Exactly. So the dot product with R is completely what's the right word? Redundant. We don't need it.
Yeah.
So bam, there's our lemma. And now
That's a
we
cool
can show
proof.
that by apparent length, because remember I took here's my U perp right here.
Right.
And I scale it down by 1 over R because that's how lengths scale. And I end up getting U perp divide R. That's the apparent length of U perp. Then I have P perpendicular. I scale it down by R because that's how length scale is by 1 over R. And I get V perp divided by R. Now I have a parallelogram vector right on my unit sphere.
Yeah.
And I cross those two things, right? I'm going to say the solid angle here is equal to U perpendicular divide R cross V perpendicular divide R. That's the apparent length crossed with the apparent width. So we've got it to that point. Then, of course, R and R are scalars. So they can just be multiplied together to make R squared. And then U perp cross V perp becomes our cross product.
Oh.
So by our lemma, solid angle is defined as the integral that we have. That pattern that we're dealing with is solid angle. So whatever this integral is doing to calculate circulation, it can be understood in solid angle or how much of a spherical area is taken up.
Okay.
And I think with that, it would be fun. Let's see, where are we at? One more. I think we might have to cut this though, because we're running low on time. Would you be able to
That's not
meet
a problem.
again to talk more?
Yeah, of course.
Cool, cool. So now we finally get back to kind of the problem, right?
Yeah.
So I have to keep noting it. dW and dP are exaggerated for effect. In truth, they're infinitesimals and obey local linearity. So those small angle approximations work. Okay. So here's a drawing of a current wire and the amp loop path.
Okay.
And what I want to draw your attention to is a starting position on the wire and a small step dW on the wire.
Okay.
So that small wire displacement. I kind of want you to imagine that you're walking the wire. So
Okay.
you're standing on the wire, you're, the size of an ant, and you're looking at the amp path, and you take a small step dW, and you're trying to kind of see how this enneagram plays out.
Okay.
So if you take a step dW, oh, hang on 1 second. I think the air pressure pushed the door open there. Lots of strip. All right. So this is your initial position right here.
Yeah.
You picked a place on the wire, and you're standing on the wire, and you're looking at a small little piece of the amp path, small little displacement dP.
Sure.
And you note to yourself, you say, this seems to take up this much apparent length.
Uh-huh.
dP perpendicular scaled down by R. So now you know exactly, well, you don't even need to do the math, right? You know what it looks like. You're used to
Yeah.
looking at things.
Mhm.
Then you take a step. And as you take the step, you keep your eye fixed on dP.
Mhm.
And dP appears to sweep across. The projection of dP appears to sweep across your field of vision.
Right.
And the amount it sweeps across by is equal to dW perpendicular divided by the magnitude of R.
Sure.
Then, to figure out the total solid angle that was swept out by that single dP as you took step dW, we do the same thing, right? We take the cross product of the apparent lengths and widths. And we end up with this, which by our lemma is equal to this, which is exactly the integrand that we're dealing with.
Right.
So whatever this integral is doing, it is somehow tracking how the amp loop path sweeps over the unit sphere from your perspective, walking the
Interesting.
wire. And I think that's probably a good spot to call it for now.
Okay.
Because that's the big breakthrough, right? Is this disgusting, nasty for loop integral with
Uh-huh.
infinite times infinite possibilities ends up reducing to what does the amp loop path look like and how much solid angle does it sweep out as you walk?